Chapter 15 homework. And for this one, we worked from the bottom to the top, so I'll start with the bottom. So for question 10, we have a 3-inch radius disc spins at a constant rate, omega 2 is equal to 4 radians per second, about an axis held by a housing attached to a horizontal rod that rotates at a constant rate, omega 1 equals 5 radians per second. Know that theta equals 30 degrees. Determine the acceleration of point P on the rim of the disc. So here we have our rotating frame is omega 1, and that's equal to 5 radians per second in the I direction because it's rotating over the x-axis. And our omega 2 is 4 radians per second. That's K because it's rotating about the z-axis. So we can write our omega vector as 5I plus 4K. And our alpha is equal to our rotating frame times omega 2, and our rotating frame is just omega 1. So it's the cross product between omega 1 and omega 2, which just comes out to be 5 times 4j. So it's going to be negative 20j because of the way we orient the I minus j plus k. So the position vector to point P, the disk has radius 0.25 feet, and P lies at theta equals 30 degrees. So just splitting this into the components along the I and J directions, we get RP is equal to 0.2165I plus 0.125J. The velocity of the P is equal to our omega vector times our RFP vector, or not times, sorry, the cross products. We compute the cross product and we get the velocity vector of P is equal to negative 0.5I plus 0.866J plus 0.625K feet per, those are all in feet per second. And then the acceleration of P, we just kind of broke this down into 2 separate components and computed those cross products individually, added them together, combined like terms, and final answer for acceleration of P is equal to negative 3.46I minus 5.125J plus 8.66K. That's all in feet per second squared. For problem number 9, knowing at the instant shown the rod attached A has angular velocity, so omega of 5 radians per second, counterclockwise at an angular acceleration, alpha of 2 radians per second square, clockwise, determine the angular velocity, the angular acceleration of the rod attached at B. So let's see, I think I started up here, is 5 radians, started up here. So we're given that the rod AP rotates with an omega of 5 radians per second and alpha of 2 radians per second squared. The length of AB is 0.2, and we're given different angles that they make. So just doing triangular geometry using law of sines, we can get the distances of AP and BP. And then our position vectors are here, just getting those into the correct directions in the X and Y, or I and J. Then we come down here, we're doing the velocity of P from the AP rotation. It's just computing cross products, and acceleration is just another 2 cross products. Then you combine the tangential and centripetal accelerations, and you get the total acceleration of negative 2.3265I minus 6.2467J meters per second squared. Question 8. A 3-inch radius drum is rigidly attached to a 5-inch radius drum as shown. One of the drums rolls without sliding on the surface shown. The cord is wound around the other drum. Knowing that at the instant shown, and D of the cord has a velocity of 8 inches per second and acceleration of 30 inches per second squared, both directed towards the left, determine the acceleration of point A, B, and C on the drum. So we're given outer radius, inner radius. We know that the velocity of D is equal to the velocity of B because it's going in a straight line along the rope. And that's 8 inches per second. And we can say that the acceleration at D is also equal to the acceleration at B, which is 30 inches per second. So finding the angular velocity, omega, we get 4 radians per second. Angular acceleration, we get 15 radians per second. So the acceleration of point A is r omega squared, which is 48 inches per second squared vertically. The acceleration of point B is, where is it? It's down here, 85.4 inches per second squared, and theta is tan inverse of 80 over 30, which is 69.4 degrees above the horizontal. And for our acceleration of C, you get 82.8 inches per second squared, and theta is tan inverse of 75 over 35, which is 65 degrees. And that's above the horizontal. Question 7. Knowing that at an instant shown, crank BC has a constant angular velocity of 45 RPM clockwise, determine the acceleration A of point A and of point D. So, acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B in the tangential and in the normal direction. And I just split them into different components in the top and solved all the way through for alpha AB. And then used that, plugged it back in to get alpha A as 51.3 inches per second squared downwards. And the theta is 16.1 degrees above the horizontal. And the acceleration from B to D, you can have acceleration of B is equal to 88.827. And so we can write that in terms of acceleration of D with respect to B. And then we can solve for acceleration of D is equal to 184.9 inches per second squared at 16.1 degrees above the horizontal. I think I said that the acceleration of A was at 16.1, but it's the acceleration of D. Acceleration of A is just directly downward. Question 6. Arm ABC rotates with angular velocity of 4 radians per second counterclockwise, knowing that this angular velocity of the intermediate gear B is 8 radians per second counterclockwise. Determine the instantaneous centers of rotation of gears A and C, the angular velocities of gear A and C. So velocity is given as omega times radius. And here, the radius between both are the same. And ABC is rotating with the same speed. So that's where we get these 1.2 meters per second up and down. And then omega A is just equal to 4 radians per second. Omega c is 2 radians per second. Gear B is in contact with both gear A and C, as you can see up here. So I did 1 and 2 where they're connected, and the radiuses for these are switched because it's just the distance, or like, yeah, it's the distance that it has to travel in the opposite direction for it to line up. So we have our V1 and V2 at those points, and we get 1.6 meters per second down and 0.8 meters per second upwards. In our instantaneous center, we get our velocity over angular velocity. So these are just the velocity of the points. So we get 1.2 over 4, or 0.3 meters. And for C, we get 0.6 meters, or 600 millimeters. All right. So both 6-inch radius wheels roll without slipping on the horizontal surface. Note that the distance AD is 5 inches. The distance BE is 4 inches, and D has velocity of 6 inches per second to the right. Determine the velocity of point E. So since D rolls without slipping, you can relate the translational velocity to the angular velocity. So we come up with this equation here, and we get our angular velocity of D is 1 radians per second. So we now know that it's rotating, and A is at 5 inches above the center of D. With the velocity of A is equal to omega D plus RA respect to D. This is 11 inches per second, the answer, but this is 11 because A is 11. D is 6 inches off the ground, and A is 5 inches above D. So that total effective radius is 11 inches. And then we come over here to find B. My work's kind of messy up here. So we find our velocity of B in the I and J components. And here we just have a couple equations on the bottom and up here. And it's basically just plug and chug. You have to solve a system of equations. That's what I did down here. So you get it in terms of WAB, and you plug it in and solve all the way down. And I got V of E to be negative 14.76 I, which would be 14.76 to the left. When I was looking at the answer key, I saw that it was 14.76 to the right. And I was just thinking about it this way. If these two were connected like how they were, and A is going to the right, it would force this bar to come down, and pushing B, pushing point B down, this whole right side would shift to the left, pushing point E to the right. So I'm not sure how it's going. Or pushing point E to the left. Sorry, not right. So I don't know, maybe I'm thinking about that wrong, but for 4, knowing at the instant shown The angular velocity of rod DE is 2.4 radians per second clockwise. Determine the velocity of A and the velocity of point B. So we're given omega of DE, and so it moves in a circle about E, so we're able to calculate the velocity. So the velocity of D is 288 J upward. The velocity of A, this is just split into different components, I and J components. We get velocity of A is equal to 540 millimeters per second to the right. And here's my work for the velocity of B. And we get V of B is equal to 457 millimeters per second at 61.8 degrees above horizontal. Question 3, disk shown moves in the xy plane, knowing that VAY is equal to -7, VBX is equal to -7.4, and VCX is equal to -1.4. Determine the angular velocity and the velocity of point B. So we're defining the position relative to point A. The radius is 0.6 meters, R of B with respect to A, and R of C with respect to A. We have our general equations over here, and then this is just me computing the cross products for A or for B and for C. We come out with these equations down here and here. And we can use our knowns, what we're given below here, plug them into our equations, and solve all the way down. So we get our final angular velocity to be 10 radians per second counterclockwise, and our velocity at B in the y equal to what we just have, -7.4 I minus J. For question 2, a load to be raised 20 feet or 120 inches by the hoisting system shown. Assume gear A is initially at rest, accelerates uniformly to a speed of 120 RPM in 5 seconds, then maintains constant speed of 120 RPMs. Determine the number of revolutions executed by gear A in raising the load and the time required to raise the load. So step 1, it starts at rest, so the initial angular velocity is 0 and accelerates uniformly to a final angular velocity of 120 RPMs or 4 pi radians over 5 seconds. So angular acceleration is given as this, angular displacement, and the angular displacement at a constant speed, you split it up into 2 different sections, when it's accelerating and when it's at a constant speed. So we're finding the angular velocity at the constant speed, which we already know, and we are just calculating how long it takes for the time. And total time is time of the acceleration plus time of the constant, which is 10.139 seconds. Oh, and the number of revolutions is... where did it go? Oh, the number of revolutions is up here. We started with that. And then question 1, 2 pulleys shown may be operated with the V belt in any of the 3 positions. If the angular acceleration of shaft A is 6 radians per second squared and the system is initially at rest, determine the time required for shaft B to reach a speed of 400 RPMs with the belt in each of the 3 positions. So we're given the angular acceleration and angular velocity of B. We're just given the angular acceleration of A, though. we're able to convert that to radians, and then we have to like relate relate the gear ratios pretty much. And so since A starts at rest, we can write the equation omega A is equal to alpha A times T. And the belt speed constant, we can rewrite it in this terms to solve for time. So at belt at left, we have time is equal to 3.49 seconds. Belt in the middle, we have time is equal to 6.98 seconds. And belt at the right side, we have 13.96 seconds.